Hello and welcome to Sampling Theory and the Central Limit Theorem. In this video, I'm going to be sharing three different things with you. First of all, the big idea with sampling, and then I'm going to show you an example of how we never actually do this, but what that would look like. And then I'll show you on the graph exactly how that plays out for different sizes of samples. So let's start off by thinking about the big idea. And the big idea about sampling is that we start with a population, and from that population, since we can't usually measure absolutely everybody in the population, what we do is we take a sample of individuals instead, and we measure them. Now, every once in a while, we do actually measure all of the population. So, for example, in vital statistics, we try to measure everybody. In the census, we try to measure everybody. But usually it would take too much time, it would take too much money, too much effort, and a sample will often get us very similar results. And so that's why we do this. Now, there are a couple of caveats. First of all, this needs to be random in order for the sample to represent the population. Or, and I'll just put simple random sample would be kind of the ideal, or something that's similar to that. So if we take a sample that is not random, that is somehow does not represent the population, then whatever we find in the sample, we cannot then say anything about the overall population. So it's important that this is a random sample. Now once we get this sample, what we do is then we measure something. And a lot of times the thing that we measure is one of those kinds of variables: nominal, ordinal, interval. We measure person, place, and time. We measure disease. We measure all kinds of things about that sample. And the reason that we measure it is so that then we can go back and infer something about the population. So we measure the sample so that we can make an inference about the whole entire population that that sample came from. Now, a couple of key points here. One of them is that this randomness introduces an element of chance. And this is everything about what we're going to be talking about today. That element of chance, that sample, is not necessarily exactly like a miniature version of the population. It might be slightly different just because of the chance surrounding selecting a small group of people out of the population. The other things that we need to define and talk about really quickly before I move on to the next part is what these measures and inferences are called. And so the thing that we measure is called a statistic. And the thing that we infer about the population is called a parameter. And so we have population parameters, we have sample statistics, and let me give some examples about that. The parameter might be the mean, and we designate that by the Greek letter mu. The statistic that we measure about the sample is also a mean, but we designate it with an X bar. If we're thinking about proportions, we might have the population parameter, and then the sample statistic would be p hat. And so notice that we often use a letter, but it has kind of a designation about it. In the population, we measure standard deviation, and that is signified by the Greek letter sigma. And in the in the sample, we measure the standard deviation. A lot of people will call that S. A lot of times I'll refer to it, that's an equals. I'll refer to it as SD, that's a lowercase s. I refer to it as SD because a lot of times you'll see it referred to in in published literature as SD equals standard deviation. So just know that both of those things count as the statistic for standard deviation for the sample. Now, So that's the big idea, is that we start with a population, we take a sample, we measure things about the sample, and hopefully, let me add one more thing here, this measurement needs to be somewhat accurate in order for our measurement then to infer something about the population. And that sample is selected randomly, and there is some element of chance then about what kind of sample statistics we'll get, like the mean and the standard deviation and so forth. Okay, so next I want to play a game called We Never Do This. And we play this game a lot in statistics. Other people play Jeopardy or Who Wants to Be a Millionaire? We play We Never Do This. So in this particular version of the game, we are going to take multiple samples from the population. Now remember back when I said, why do we take a sample? We take a sample because we don't have the time or the money to measure everyone in the population. So we would not do this. We would not take multiple samples from the population. It would take more time and money. So in a typical study, we only take a sample, one sample. Remember when we talked about study design? We're only talking about one sample of group of people or whatever. So in this We Never Do This version of this game, we are going to take multiple samples from the population. And it's for the purpose of understanding sampling theory and where we get this central limit theorem from. So here we are, we're taking multiple samples from the population. And what we know is that for each of those samples, the x bar is going to be different, or the mean. So we take a sample of size 4, and we get a mean of a certain number, and then we take another sample of size 4 people, and we get a different sample mean. And so those sample means will actually vary. If we take all of those sample means and make a histogram of them, then this is called the sampling distribution of the means. And this sampling distribution of the means, this histogram of all those x bars, has, just like every other histogram, has a shape, it has a location, and it has a spread. And so here we are, and I'll actually use the graph over here on the right-hand side. Let's say we take a sample that has, let's pick 4 people. 1, 2, 3, 4. And those 4 people actually have a mean somewhere around in here. So I'll put the little x bar here. If we were to put those people back, and instead of those 4 people in our sample, we took a sample and let me pick a different color. Let me make this one orange. Let's say we pick 1, 2, 3, 4. And we got those 4 people, and that was our sample of 4 people. That would have a different sample mean. So here's our sample mean for that particular sample. And if I had lots of colors, I could show you this whole idea of taking multiple samples from the population. And so let's just say that we do that over and over and over and over and over and over again, hundreds of times. And what you would find is that we end up with these sample means that are kind of spread out, and they tend to kind of group around the middle. Some of them are dead on, some of them are kind of far out. I'm just going to keep drawing them here so that you can get the idea. So here's, like, I'm taking this population and I'm sampling it over and over again. I'm not drawing very good x bars, sorry about that. So here I'm trying to fill in like approximately where they would land. Let's say there's one here, one here, one here, one here, one here. So I'm just sampling over and over again, and I'm getting lots and lots of x bars. I get one there, I get one here, maybe I get one there. Maybe I get one way out there. Every once in a while you get one that's kind of far away. So if I just randomly pick 4 people out of that population, I'm going to get all kinds of means for all of those samples. And the thing that we notice when we actually do this as an exercise, remember we never do this in real life when we're running, doing the kinds of normal surveys and that kind of thing. The thing that we find out is that the shape of this tends to be symmetrical, and it tends to be normally distributed. And I'm going to put a capital N because that stands for normally distributed. And the location tends to center on the population mean. Remember, this is the population mean. Here's the population mean. And the spread is less spread out than the population. And we actually give a name to this amount that it's spread out, and it's called the standard error of the mean, or just plain old standard error. So here we have an amount of spread out that's, and I'll just kind of draw it here. The majority of our means are kind of within this range right here. But that's less spread out than our original population is spread out. See how that's narrower? And that makes sense, because if we pick 4 people, they're going to randomly fall on both sides of the mean. Only every now and then would we have randomly select 4 people that are all farther to the right or all farther to the left. So those 3 things we know about this sampling distribution of the mean. It tends to be symmetrical or normally distributed. It tends to center on the mean for the population, and it is less spread out than the population is, and we call that the standard error. So let's specifically look at all 3 of those things. First of all, in terms of the shape, the sampling distribution of the mean tends to be normally distributed whether or not the population itself is normally distributed. And so if that makes any sense at all, what that means is that if I'm picking 4 people out of this population, they're equally likely to fall to the left or to the right of the mean for that particular population. And so that is actually a concept called the central limit theorem. And the larger that sample size gets, the more and more and more true that particular rule holds. The sampling distribution of the means tends to be normally distributed whether or not the population is normally distributed. So here's our population distribution. And here's our sampling distribution of the mean. Let me make it orange. There's our population distribution. So that is called the central limit theorem, and I'll just go ahead and put that right here. Central limit theorem. So the shape of that sampling distribution of the mean tends to be normally distributed, and it becomes more and more and more so the larger the sample size. So this sample actually has a sample size of n, and that's a lowercase n. In terms of this location, some interesting things about the location, it centers on the population mean, and what that means is that it's equally likely to be larger or smaller than the population mean. Another way of saying that is that it is an unbiased estimate of the population mean, and that's a really important concept as we're moving forward into hypothesis testing, is that if we know something about the sample mean and we know that it's an unbiased estimate of the population mean, then it legitimizes the fact that we're making this inference from the thing that we measured before. So this is unbiased. And then in terms of the spread, this sampling distribution of the mean is less spread out than the underlying population, and that is based on this standard error. Now this is a concept that's going to take a little bit more space, so I'm going to go ahead and write that up here. The standard error is equal to the population standard deviation divided by the square root of n. And this has a special name to it, and I'll again write it in red. This is called the square root law. So we're going to use that standard error in order to do an example now. So, quick recap. From a population, we take a sample. The sample, we measure things, and from that we can infer back to the population. Now, in order to understand some things about that particular sample, we're going to play a game that's called We Never Do This. We take multiple samples from the population, and each of those has its own mean, each sample. When we make a histogram of all of those sample means, it starts behaving like the normal curve that we are used to. So I have both of those curves superimposed on each other here so that we can do kind of like our regular activity that we like to do regarding normal curves. So here we have, and let's go ahead and put this in green, here we have the population distribution. Now that's this one right here, population distribution. Its shape can be all kinds of things. Its location is the mean, called mu, and its measure of spread is sigma. And so if we think about the whole rules of kind of how this is spread out, here we have our 95% confidence interval. Here's mu plus 1 sigma. Here's plus 2 sigma. Here's minus 1 sigma. And here's minus 2 sigma. And remember, between these two areas right here, that's 95% of the population will fall within that middle range. And then 2.5 falls into this tail and 2.5 falls into this tail of the population. So right now we are back at talking about this population. If we were to apply z-scales or z-scores to that, we would say a z of 0 is equal to the mean, a z of 1 is 1 standard deviation above, a z of 2, here we have a z of minus 1 and a z of minus 2. And let's go ahead and apply all of that to our IQ example. Remember, the mean IQ is 100. If we go, remember the standard deviation of IQ is equal to 15. If we go plus 1 standard deviation above, that would be 115. Plus 2 standard deviations is 130. Minus 1 standard deviation below would be 85. And minus 2 standard deviations below would be 70. Whoops, that's 0, sorry. So that just gives us a shape for our underlying population. Now we're going to play this game where we take multiple samples from the population of sample size 4. And so I'm going to signify those with our nice orange color. So now here we have a sampling distribution of the mean for a sample size n equals 4. And what we know about that sampling distribution of the mean is it also has a shape, it has a location, and it has a spread. So that's this one right here. That's all those x bars. The shape, remember we learned that the shape tends to be normally distributed. So the shape is normal. The location, again, tends to center on where the population mean is. So here's our mean. And the spread is equal to the standard error, which is this population standard deviation divided by the square root of n. So let's go ahead and draw that. And so here we have our sampling distribution for n equals 4. The location is mu. So the mean for that is actually also the mean that we saw in our population. The spread out is going to depend on how we calculate this standard error. So let's go ahead and calculate that. Our standard deviation of the population is 15. And here we have a sample size of 4, and I did that just so that it would be easy to take the square root of 4 as 2. So 15 divided by 2 is 7.5. So here we have plus 1 standard error, plus 2 standard errors, minus standard error, minus 2 standard errors. And remember, it's narrower than our underlying population. So this can also have a z-score of the sampling distribution of all of those means. And it too would have a z-score of 0, 1, and 2, minus 1, and minus 2. Just notice that this whole entire thing is narrower than how far distributed the whole entire population is. It narrows as we increase our sample size. So let's go ahead and show what that would do for our actual sampling distribution of the means. The mean of the means is, again, 100. Remember, the location is the mean. The spread is determined by the standard error. So plus 1 standard error is plus 7.5. So 107.5 plus 2 standard errors is 115. Minus 1 standard error is 92.5. And minus 2 standard errors is equal to 85. So you can see that with a sample size of 4, we now have a different distribution than the underlying population. If we were to repeat that with, and let's just use another color. Let's say we have a sampling distribution that has an n is equal to 4, or sorry, not 4, 16. We just did 4. N is equal to 16. And again, I'm choosing numbers that will easily, we can take the square root of pretty easily in our heads. So let's say we need the standard error for that particular population. It's equal to sigma divided by the square root of 16, which is equal to 15 over 4, which is equal to 3.75. So let's go ahead and map that out. Again, we would have a mean plus standard error plus 2 standard errors minus standard error, and I'm going to have to like zoom in, or I can't draw that small, minus 2 standard errors. Let's make our... So here again, we have a z-score of 0, 1, and 2, minus 1 and minus 2. And as it turns out, remember how we calculated our standard error is equal to 3.75, so plus 1 standard error. Here we have 100, plus 1 standard error is 103.75, and plus 2 standard errors is 107.5. And you could do the same thing minus standard errors. So minus 4 would be 96, so 96.25, and then 92.5 would be minus 2 standard errors. And an interesting thing starts happening as you increase the sample size. As you quadrupled the sample size from 1 to 4, basically, your the width of your 95% confidence interval got cut in half. So it went from 70 to 130 down to 85 to 115. As we quadrupled that again from 4 to 16, our 95% confidence interval again got cut in half. And so every time you quadruple the sample size, then your standard error gets cut in half. And that makes perfect sense because it's the square root here that's on the bottom of that standard error equation. If you think about it, as the sample size gets bigger, even intuitively, we become more and more and more sure of this middle line that kind of traverses the right down here through the middle. And so what I like to think of this is, I could have renamed this particular video the magnet of the mean. And what I mean by the magnet of the mean is that as our sample size gets larger and larger and larger, each one of these means gets sucked closer and closer and closer to this middle value. And that's totally dependent on this sample size, n, of the sample that we have drawn from that population. The larger that sample gets, the closer and closer we can be sure that we're going to get an X bar that's pretty close to the actual population. The extreme of that is when we draw a sample size that is equal to the entire population, and then we know for sure that our mean is equal to that of the population. So this curve that's the standard, that's the sampling distribution of the means, just gets narrower and narrower and narrower the larger and larger our sample size gets. Let's do one more example down here, and let's call this n equal 100, because that's actually also another easy one to square root. The standard error that goes with that is equal to 15 over the square root of 100 over the square root of 100, which is equal to 15 over 10, which is equal to 1.5. So here we have our mean of 100 plus 2 standard errors is 103, and minus 3, because it's 2 standard errors, is equal to 97. So in this case, as soon as we have a sample size, it's an n equals 100, then 95% of these X bars are going to fall between 97 and 103. You see the value in that? Instead of being so spread out between 85 and 115, as we had with our sample size of only 4, the larger and larger the sample size, the narrower and narrower this gets. So if we had a sample of 10,000, then obviously it would be even much narrower. And so that is actually something that is called the law of large numbers. And so I'm just gonna draw one more thing here on our curve. Let's imagine that the green, again, is our population. I'm going to draw a sample. Let's say we drew this sample. Here's the sample distribution, and it has its own shape. It has a location. It has spread. We knew that the spread here is the standard deviation, the location is X bar, and here's the law of large numbers. If the larger and larger our sample becomes, what the law of large numbers tells us is that our sample mean will get closer and closer and closer to our population mean. That's exactly what we see. So really, these two things, the whole idea of standard error being inversely related to the sample size and the law of large numbers also being related to the sample size, and here we have the central limit theorem being related to the sample size. As the sample size goes up, the shape of the sampling distribution of the mean tends to become more and more and more normal. even if the underlying population shape is not. As the sample size goes up, the standard error becomes smaller and smaller and smaller. In other words, the width of this curve gets narrower and narrower. As the sample size goes up, this law of large numbers tells us that the mean tends to get closer and closer and closer to the actual population mean. Now, a couple things just to wrap up details. The shape of the population distribution can be already normal, or it can be not normal. And if the shape is normal, then the shape of the sampling distribution also tends to be normal. If it is not normal, then we depend on the central limit theorem, which says that we need to have an adequate sample size, especially the larger and larger the sample size, then this will also be normal. And usually we think of that as 30 or more subjects in our study. So it doesn't have to be huge. Obviously, the larger and larger it gets, the more and more that central limit theorem begins to hold. Also, the shape of the sample distribution tends to reflect the shape of the population distribution. And so if we take this random sample from our population, this sample tends to have the shape of that parent population. And so those are a couple of things to keep in mind. Let's see. I wanted to talk, just close up about this whole idea of the standard error. I want this to not just be something that you memorize. I want the idea that the standard error is related to the square root of n and to the overlying parent spread to be intuitive. And so think about it this way. If we have our overlying parent population is spread out a certain amount, then it makes sense that if we are to increase the amount that that's spread out, that the standard error would go up. Said in the opposite way, if we decrease the overall parent population to something where it's a little bit more narrow, then it also makes sense that this standard error would go down. So let me erase those just to get rid of the confusion. Let's talk about the sample size then. If the sample size goes up, if you just ask somebody, if I collect a bigger sample size, do you think I would be more sure of my results from my study? And most people would say, oh yeah, if you collect a tiny sample size, maybe you're not very sure. But if you collect a larger sample size, then you're more sure. And so that goes along with here having a larger sample size that decreases the standard error. In other words, we're bringing these sides in, and we're more and more sure of exactly where that curve is. So on the flip side of that, if I decrease the sample size, because maybe I don't have as much money, then it tends to be, this width right here tends to be more spread out, and so I'm not quite as sure about the results that I get, and that again is intuitive. If the parent population, sorry about that, if the parent population is more spread out, then my standard error will be more spread out. If my parent population is less spread out, then my distribution of means will be less spread out. Same thing happens inversely with the square root of the sample size. And so standard error is inversely related to the square root of the sample size. And we showed that down here when we continued making that sample size bigger over and over again. So thank you for joining me for this talk, and I hope that was helpful.